Welcome to Math with Professor V. In this video, we're going to learn about integration by parts. So first, before we talk about what the formula is or how to set up using integration by parts to evaluate an integral, we want to look at the derivation of this formula, and it comes from the product rule. So think back when you were a sweet little Calc 1 student and you were first learning how to take derivatives. We learned that when we take the derivative with respect to x of a product of two functions of x, the way I like to think about it is basically they take turns having their derivative taken. So you take f's derivative, you have f prime of x times g of x, you leave g alone, it's not his turn, plus g prime of x times f of x. And we know multiplication and addition are both commutative operations, so the order in which you write out the product rule doesn't matter, just so long as you follow the format, basically. So you can think of it like integration by parts is basically a way to figure out the antiderivative of a product of two functions. It's almost a way of undoing the product rule. So I'm going to write out loosely right now. Our goal is to integrate the following function. We want to integrate something of the following form, basically. Integral f of x times g of x dx. And we're looking at situations in which the one integration technique that we know so far, u sub, won't work. We know u sub we use when we have a composition of functions. U sub undoes the chain rule. This is a different scenario. So I'm going to let capital G of x be any antiderivative of lowercase g of x. And you've hopefully seen this notation before. When we use capital letters a lot, that represents the antiderivative of some function. So what does it mean if capital G of x is an antiderivative of lowercase g of x? Well, then that means that capital G prime of x is equal to lowercase g of x, right? If I take the derivative of g prime, I get lowercase g back. So now what we're going to do, we're going to go in, let's apply the product rule to f of x times capital G of x. So I'm going to differentiate with respect to x, little f of x times capital G of x. Okay, so product rule time. F of x, I'm going to leave it alone, derivative of capital G of x, g prime of x plus, and then they take turns. So now it's f's turn, f prime of x times, leave g of x alone. Okay, but remember, g prime of x is who? That's right, g of x, lowercase. So let me replace it with lowercase g of x plus, here's f prime of x times capital G of x. Okay, now look at what just happened. I took the derivative of this function. It's a product of two functions, but it's a function in and of its own right. And I got this result. Well, think backwards. That tells me that f of x times capital G of x is an antiderivative of this messy little guy. Okay? Antiderivative means you take its derivative and you get the following function. So who's the antiderivative of this? Lowercase f of x times g of x. So let me summarize for you. So this tells me lowercase f of x times g of x is an antiderivative of this function. So what's another way I can say that? Well, the indefinite integral of that result right there, f of x times g of x plus f prime of x times capital G of x dx. Who's its antiderivative? Its antiderivative is sitting right here. Just think, whose derivative did I take to get that result? Lowercase f of x times capital G of x. Now from here, we're basically going to come up with our formula for integration by parts. I'm going to distribute the integral on the left-hand side. So I have integral f of x times g of x dx plus integral f prime of x g of x dx equals f of x g of x. And then remember, what was our goal originally? I wanted to integrate the following form. So let me isolate this integral over here. And we have f of x, g of x, dx equals f of x, capital G of x, minus integral. Good. F prime of x, g of x, dx. So here's our formula for integration by parts. You're going to be starting with the left-hand side, and then you rewrite it using our by parts formula. But to make things a little simpler, we rename the functions f of x and g of x. Let me show you. So in practice, we let u equal f of x and little v be capital G of x. Then du is going to be f prime of x dx, and dv would be g prime of x dx, which we know is our little case g of x dx. So if I use this renaming, then this formula just becomes a lot easier to recall. Let me walk you through it. So u is f of x, that's u, so you have integral u. And then lowercase g of x dx, who's that? That's dv. So integral u dv equals f of x, again, is u, times capital G of x, which is v, minus integral f prime, who's f prime? Well, we don't have f prime by itself, but we do have f prime of x dx, that's du, and then this g of x right here is v. So this integral here is v du. v du. Let me color code that for you a little bit better so you can see. So f prime of x dx, that's du right here. And then I'm running out of colors. Capital G of x is my v right here. Okay? So this is usually the way students remember it. U dv equals uv minus v du. What that means is when you're given an integral, you have to break it up so that you identify one part of it to be u, and then the other part is dv. And u times dv should always give you back the original integral, including the differential, dx, dy, whatever it happens to be, okay? And then your goal is that this ends up being some integral that you can evaluate more easily than what you originally started with. We're not rewriting it like this just for, for kicks. It's like we have better things to do. The idea is this integral we can't evaluate directly, but hopefully this one we can, or at least we get closer to being able to do so. So I'll walk you through the process. I got a bunch of examples. Hopefully you'll be a professional by the end of this video. And let's just jump into it, okay? Now, how to pick them appropriately. There's all sorts of different things. There's some tricks that, some instructors like to use. Liate or liate, I don't know, however you want to pronounce it, is one way where you use logarithmic functions. Then you have inverse trig functions, etc., etc. I don't always like doing that because I'd rather you kind of remember what the idea is behind it, what motivates you. There's another one instead of liate, what is it? Lipit. Polynomial, exponential, trig. But there's always exceptions, and I'd rather you have like a better understanding of what's going on, okay? So here we go. I'll show you a nice little setup and hopefully it'll start making sense. Evaluate the following integrals. A, we have integral of x times sine 2x dx. So I want you to set it up this way. We've got integral x sine 2x dx, okay? First of all, no u sub will help you. I'm so sorry. You can't let u be anything and then it turns out simpler, right? If you try to let u be 2x, then du is 2 dx, and then you still are stuck with this guy. So, okay, hopefully we agree that's going nowhere. Now, we have to pick u and dv, right? Look back at our by parts formula. We have to pick u and dv, but you have to pick them appropriately because we need the integral of v du to be easy to evaluate. So set it up like this. You choose u and dv, and then we have to find du and we have to find v. I want this product to be something that I can easily integrate. So I'm going to set it up badly first for you to see the difference, okay? Say I guessed and I'm like, okay, I'm going to let u be sine 2x, and I'll let dv be the rest of it. It has to be the rest of it, x dx. I want you to see why this won't work first, okay? The derivative of sine 2x would be 2 cosine 2x dx, because we have to do the chain rule, don't forget. And then how do you get from dv to v? You take an antiderivative. So antiderivative of x is 1/2 x squared. Now, from our by parts formula, this is going to be u times v. So we would have 1/2 x squared sine 2x minus integral v times du, this product here. The 2 and the 1/2 are going to cancel, and then I have x squared cosine 2x dx. Now you look and you go, did my life just get better or worse? And you say, okay, look at this integral that I have here. Does it look more simple or more like something I could integrate compared to what we started with? No, things are getting worse in the sense that we had x and now we have x squared. I'm no closer to being able to evaluate this antiderivative. So whatever we did was not right. It's time to abort mission, and we must have chosen incorrectly. So swap them around the other way. Swap them around the other way. And what does that mean? That means u needs to just be x, and dv is going to be sine 2x dx. Okay, and this is where that LIPIT acronym, sometimes people use it like, oh, the polynomial should be u, because the acronym helps you choose u. Okay, let's go from here and see if it turns out better. So you always find du and v after you choose those two. So du, derivative of x, is 1 dx. And then v, be careful, antiderivative of sine 2x. Think backwards. Whose derivative did I take to get sine 2x? Negative 1/2 cosine 2x. And you don't even have to write out the full formula. Right here, you could do just a good common sense check, because you know you're going to integrate the product of this row here, v du. Does this product give me something easier to integrate than what I started with? Yes, because notice, now I don't have x times a trig function anymore. I just have a constant times a trig function. And the beauty of by parts is when you let u be x, right, or some polynomial, du is always 1 degree lower, so you can start kind of stripping that away. Beautiful. Okay, so let's rewrite it now. What do we have? This original integral becomes uv, which we don't integrate. That's outside the integral. So that's going to be negative 1/2 x cosine 2x minus the integral of v du, which we're very excited about, which is negative 1/2 cosine 2x dx. How are you doing? Good? Okay. Now let's work on this cute little integral here. I've got negative 1/2 x cosine 2x. Take that negative 1/2 outside, so now it's positive 1/2 integral cosine 2x dx. And then now we can take the antiderivative, no big deal, right? Don't do u sub. You should be able to do this in your head. Because there's a constant in front of the x, right, in that argument, just divide by it when you take the antiderivative. So this is going to give us negative 1/2 x cosine 2x plus 1/4, because you have to multiply by a half again, sine 2x plus c. Voila. Box it with pride. That's a job well done. How was that one? We'll practice more, don't worry, okay? Here we go. Example B, sine inverse of x dx. Okay, let's set it up. U dv. You might say, I don't see a product of two functions. So you're going to think of it as sine inverse of x and then 1. Those are your two functions. Let's talk about what would make no sense. dv can't be sine inverse of x dx, and this be 1, because we have to find v. How do you find v? You anti-differentiate. Well, I don't know the antiderivative of sine inverse. That's what I'm being asked to find, so that won't work. So that's why anytime you have an inverse trig function, that's going to need to be u. Then dv is just 1 dx. Make sense? Okay, now let's find du and v. Oh yeah, you got to memorize your derivatives. Do you know derivative of sine inverse of x or arc sine of x? 1 over square root 1 minus x squared dx. Good. And then v is antiderivative of just 1, so that's x. Now you guys be careful, pay attention. Let me put the little watch out eyeballs. If you have du, you should have dx on the other side. dv, dx. These ones are not derivatives, so I don't have that. Make sure you're not missing anything. Okay, here we go. So now we're going to have u times v outside. That doesn't get integrated. So x sine inverse of x minus integral v du. So I'm going to have x over the square root of 1 minus x squared dx. Good? All right, are we any closer to making progress? Can we figure out this integral? Well, this time I can do a u sub because look, underneath the radical, I've got 1 minus x squared, that's degree 2. If I substitute all of this for another variable, then the derivative would be degree 1, which is sitting up here. Only thing is, you guys, we already used up the variable u. For by parts, we said u is sine inverse of x. So we can't be over here lying to the people and then say, oh, changed our minds, now u is 1 minus x squared. So we got to pick a different variable. The most common one to go for next is t. So let's let t be this quantity here, 1 minus x squared. And then dt would be negative 2x dx. Do I have that in my integral? Almost. I just have plain old x dx. So let me get that by itself. So negative 1/2 dt is x dx. And then now let's put it all together. So we still have this x sine inverse of x hanging out in the front, right? Minus integral. So this x dx gets replaced with negative 1/2 dt. But what I like to do is put the negative 1/2 outside my integral. dt is here. And then I'm just going to have square root of t in the denominator. So I'll write it as 1 over square root of t. Take a second. Are you okay? All right, beautiful. Now let's rewrite it so we can find the antiderivative more easily. So this is x sine inverse of x plus 1/2 integral t to the negative 1/2 dt, yeah? Beautiful. Add 1 to the exponent, divide by the new exponent, and rewrite everything as you go so you don't lose somebody along the way. So 1/2, add 1/2, it's going to be t to the positive 1/2. Divide by 1/2 is the same as multiplying by 2, and then plus c. All right, these guys cancel, and then we're almost done. Just make sure you replace t with 1 minus x squared. So we've got x sine inverse of x plus 1 minus x squared to the 1/2 plus c. And if you want, I would say maybe switch back to square roots because that's a little more conventional, but I wouldn't care on an exam. Just check with your instructor, okay? Plus c. Voila. How was that one? That's a classic problem. That's classic. And I would recommend you practice again. Try cosine inverse and tan inverse of x. Okay, same idea. Okay, here's another one. Integral of x to the 5th times natural log of x dx. Okay. I've told you lip it and liate or whatever. I'm not big on just memorizing stuff for no reason. Let's think about it this way. Whatever you pick dv to be, in the very next step, we find v, right? We have to find its antiderivative. So don't pick somebody whose antiderivative you don't know easily, most of the time. What do I mean by that? X to the fifth, I can take the derivative or integrate it, no problem. Natural log of x, I know its derivative. I could find, if u is natural log of x, I could find du very easily. If dv is natural log of x dx, do you know the antiderivative? Probably not. So that's one that we're going to derive it together. You do it by parts, but most of the time, if you have a natural log, you're going to let it be u because you can find its derivative much more easily than its antiderivative. Okay, so I'm going to let u be ln of x, and then dv is going to be x to the fifth dx. Remember, the product of these two needs to give you back the original integrand along with the differential. Okay, so du is going to be 1 over x dx, don't forget that part, and then v, antiderivative of x to the fifth. Very good, 1/6 x to the sixth. Now, the other nice thing with by parts is we don't integrate uv, right? This product goes outside the integral. So if there's somebody you don't want to deal with, make it u, because you won't end up integrating u. Look back at the one we just did, right? You're like, ew, sine inverse of x. I don't know your antiderivative. Let me make you u so I don't have to deal with you. You go outside the integral. We never integrated sine inverse of x directly, right? Okay. So let's see how this is going to go. U times v, let me rewrite it as 1/6 x to the sixth and then natural log of x minus integral. Let's put this 1/6 out front. And then I have 1 over x times x to the sixth dx. Oh, I'm hopeful. That's definitely something we can do. 1/6 x to the sixth, natural log of x, minus 1/6 integral. Now this is x to the fifth dx, right? Okay, very good. And then we have 1/6 x to the sixth, natural log of x, minus 1/6, antiderivative of x to the fifth is another 1/6 x to the sixth plus c. And then I can clean all this up. This is 1/6 x to the sixth, natural log of x, minus 1 over 36 x to the sixth plus c. Beautiful. Now, one that you should know is antiderivative or integral of natural log of x. Let's just do it. Here's this little bonus problem. Okay, so you find the antiderivative of natural log of x using the by parts formula. Yes, you do. So we're going to let u be our only choice, natural log of x, and dv is 1 dx. So what would du be? Very good. 1 over x dx. And v? Just remember, this is a 1 that we're not writing, so antiderivative of 1 is x. So this is going to be uv, that's x ln of x, minus integral v du. So I have 1 over x times x dx. Well, 1 over x and x cancel out, so it's just 1. And that antiderivative is x, good, plus c. So that's how you get the antiderivative of natural log of x. Or natural log of whatever. If there's more going on than just plain old x, still kind of set it up this way. Most of the time, that's how it's going to play out. Okay? This antiderivative, if you want to just memorize it, you can. Depending on how much math you're going to do in the future, it might be helpful to memorize it. Like my differential equations class, most of them just memorized it because it comes up so often and they don't want to do this every single time. Okay? Up to you though. Up to you. All right, now let's do some with limits of integration. Okay? Here we go. We have integral from 0 to 1, x squared plus 1 times e to the negative x dx. So what do you think we should let u be, and what do you think we should let dv be? Always remember, you want du and v to be as easy as possible to integrate. And if you have some polynomial, usually you want that to be u, because when you take the derivative, it goes down a degree, so it becomes more simple. So let me let u be x squared plus 1, then du would be 2x dx. And then dv is going to have to be the rest, e to the negative x dx. Antiderivative would be negative e to the negative x. Are we okay? Oh, good. Oh, good. Okay. So from here, let's see what we've got. uv, I'm going to write that as negative on the outside, x squared plus 1, e to the negative x. Now that I'm not going to integrate anymore, right? So I have to remind myself this needs to get evaluated from 0 to 1 minus integral 0 to 1 of v du. And since there's a negative 2, I'm going to change this to positive and put the 2 outside. X e to the negative x dx. Are we okay? All right. Now, at this point, you look and you go, wait a minute. I don't know this antiderivative easily. I still can't do like a u sub. But before you have a panic attack, you look back at the original integral and you go, is my life getting better or worse? And I would say better, because we started with degree 2 times an exponential function, and now we've got degree 1 polynomial times exponential function. So the degree is going down. It's not gone down enough where I can directly evaluate this guy, but all I need to do is apply, that's right, by parts one more time, and I can. So that will happen sometimes, that you need to apply integration by parts more than once in the same problem in order to keep reducing the degree or simplifying until you get to the point where you can integrate. And how do you know to keep going? Just check, are things heading in the right direction? We went from degree 2 to degree 1, so it's not like I chose incorrectly. I'm making progress. I'm just not all the way there yet, okay? However, we already used up the variables u, v, etc., so we got to call them something else. Usually we just add a bar. So we have u bar, dv bar, du bar, and then v bar. So again, u bar should just be x. dv bar is going to be e to the negative x dx. And then du bar would be dx. And then v bar would be negative e to the negative x. All right, so let's see. We've got negative x squared plus 1, e to the negative x. I need to evaluate that from 0 to 1 later. Plus 2 times, okay, let's do this carefully. U bar v bar is negative x e to the negative x. This is also evaluated from 0 to 1. Minus integral 0 to 1 of v bar du bar. Here's another minus sign, so let me change this guy to plus, and then it's just e to the negative x dx. Close this up. Okay. How are we? Can we evaluate that antiderivative? Yes. You don't need to use sub. Just divide by that extra negative. And then I'm also going to distribute the 2, okay? And then we're almost there. I know it's messy, but just take your time. Stay nice and neat, okay? Negative x squared plus 1, e to the negative x. I'm going to distribute everything through. Minus 2x e to the negative x. This antiderivative is going to be negative e to the negative x, but then I'm multiplying by 2. So I'm going to have minus 2 e to the negative x, and now this whole mess gets evaluated from 0 to 1. Now, I'm noticing something because I just want to make my life as nice as possible before I evaluate it, these limits of integration. I can factor out e to the negative x from everybody. Did you see that? And if I take out e to the negative x, then I would have negative x squared minus 1 minus 2x minus 2, which is negative x squared minus 2x minus 3. That's just going to be a lot less terms running around on my paper to plug in those limits of integration. So let's do it that way instead. So this is e to the negative x times negative x squared minus 2x minus 3, evaluated from 0 to 1. So upper limit first, e to the negative first times negative 1 squared minus 2 minus 3 minus lower limit e to the 0, 0 minus 3. What's this? Negative 1 minus 2 minus 3, negative 6. So this is negative 6 e to the negative first. And then this is 1 times negative 3, but I'm subtracting it, so plus 3. Okay, and if you didn't notice to factor and whatnot, you should still get here, even if you left it in this messy form. It just might be a little more dangerous, okay? But you can do it, so just try. All right, good, you guys. Let's try a few more, okay? I think this next one you can try on your own. Why don't you pause the video? See if you can do it on your own. It's not as bad as the last one we did, okay? And we've done something similar. Did you try it? I hope you did. So how should we pick u and dv? If I see a logarithm, majority of the time I throw that in for u. Then dv has to be the rest. dv has to be 1 over rad x dx, which let's remind ourselves, that's x to the negative 1/2 dx. And then we need to find du and v. So derivative of ln of x is 1 over x dx. And then antiderivative of x to the negative 1/2, add 1 to the exponent, divide by the new exponent. Okay, and then just do a quick check. Am I happier to integrate this product here, v du? I sure am. Okay, so things look like they're on the road to success. Here we go. uv 2x to the 1/2 ln of x, evaluated from 4 to 9, minus integral 4 to 9 of v du. I always take the constant outside, and then you have 1 over x times x to the 1/2 dx. Okay, so now let's start cleaning up. 2x to the 1/2. You need to write that this gets evaluated, from 4 to 9, but you don't have to do it until the very end. Minus 2 times the integral 4 to 9. Now this is x to the negative first. This is x to the 1/2, so that's going to give me x to the negative 1/2 dx. Oh, we can do that, no big deal. 2x to the 1/2 ln of x minus 2 times antiderivative of x to the negative 1/2 is 2x to the 1/2. So you know what, would you allow me? No, it's okay, I won't skip steps. 2x to the 1/2, and then now this all gets evaluated from 4 to 9, right? Now I've taken all my antiderivatives. Okay, just to make it a little easier, let me write this as 2 rad x ln of x minus 4 rad x, if that helps you, from 4 to 9. And then let's see what we have. This is 2 times square root of 9 is 3, ln of 3, minus 4 times 3, that's the upper limit, minus lower limit would be 2 times square root of 4 is 2, ln of 4, minus 4 times 2. So what do we have here? This is 6 natural log. Oh my goodness, I'm so sorry. This should be a 9. Were you yelling at me through your screen? My apologies. There's no square root on that one. So 6 ln of 9, please forgive me, minus 12, minus 4 ln of 4. Oops. Minus 4 ln of 4 plus 8. Okay, I would say let's just combine the negative 12 and the 8. So 6 ln of 9 minus 4 ln of 4 minus 4. That should be good. Beautiful. Did you get it? Did you try it on your own? I hope you did. I hope you did. Okay, I have 2 more. They're a little spicier, okay? Here we go. Definite integral from 0 to 1 x cubed over the square root of 4 plus x squared. What we actually need to do is make a substitution first, and then let's set up by parts. So when I say a substitution, I mean basically like a u sub, but I'm not going to use the variable u because I'm trying to save it for when we do by parts. Do you know what I mean? So I'm going to come in here. Again, let's use good old t. Let's let t be x squared. And dt would be 2x dx. And you might be saying, Professor V, we don't have that. Well, hold on a second. This is 0 to 1. I want you to think of that x cubed as x squared times x. I'm going to put that dx up there with it over square root 4 plus x squared. Now can you kind of see it? Okay. So then 1/2 dt would be x dx, which I do have right here. Oh, okay. Then this x squared is t. This is t. So it looks like we can make that substitution. We also need to change our limits of integration. 0 and 1 belong to the variable x. I need to figure out what they are in terms of t, but 0 squared and 1 squared stay the same. So lucky for us, we have the same limits. So t of 0 is 0 squared, which is still 0. And t of 1 is 1 squared, which is still 1. That does not always happen, okay? So please check. So let's rewrite this integral now, all in terms of t. It's 0 to 1. This x squared, I'm going to replace with t. This x dx is 1/2 dt. So let me put the 1/2 outside. dt goes here over square root 4 plus t. Now, if you're pretty profesh, you might skip this step, okay? And just go straight to by parts. Some people can handle that. I'm recommending you simplify it a little bit just because you guys are just starting off learning these integration techniques. All right. Do you feel okay? Let's try setting up u and dv. I'm going to go in, let u be the polynomial sort of that we see, right? Technically, just plain old t is a polynomial, a boring one, but it is a polynomial. And then that means dv would have to be the rest of everything, dt over the square root of 4 plus t, which is the same as 4 plus t to the negative 1/2 dt. Okay, let's see if this gets us anywhere. So du would just be dt, and v, antiderivative here, since we just have a 1 in front of the t, you can just take the antiderivative and keep 4 plus t together, like a little family. We don't need to do like another substitution. Hopefully you've noticed that by now. Add 1 to the exponent, divide by the new exponent, and keep this little family together. So you're going to have 2 4 plus t to the positive 1/2. Now, can you take the antiderivative of this product more easily? Absolutely. So let's do it. So we've got 1/2 times uv, so that's going to be 2t times 4 plus t to the 1/2, that's evaluated from 0 to 1, minus integral 0 to 1 of v du, I'll put that 2 outside, and then 4 plus t to the 1/2 dt. Okay, take a second. Are you all right? Good, good. Let me leave. Actually, no. Let me distribute that 1/2 through, because look. It's going to cancel with these 2's and just be gone from our lives. Great. So this is t times 4 plus t to the 1/2 minus, now look here, I'm going to add 1 to the exponent, divide by the new exponent, all the while just keeping 4 plus t together like one happy family. 3/2, 2/3, yes? And this all gets evaluated from 0 to 1. Wow, wow, wow. Love it. Okay, now let's plug in our limits of integration. So upper limit, this is 1 times 4 plus 1 to the 1/2 minus 2/3 times 4 plus 1 to the 3/2. That's the upper limit. Minus lower limit's just going to be 0 minus 2/3 times 4 to the 3/2. Ooh, okay. So this is square root of 5 minus 2/3 times 5 to the 3/2 minus 0 plus 2/3 times 4 to the 3/2. Okay, so let me rewrite this. This is square root of 5 minus 2/3. 5 to the 3/2, that's 5 to the first times 5 to the 1/2. So it becomes 5 square root of 5 plus 2/3, 4 to the 3/2, you take the square root of 4 and then raise it to the third power. So square root of 4 is 2, 2 cubed is 8. All right, how do we feel about this? It's a gross little answer, but it's correct, so you should love it. So we have 1 square root of 5 minus 10/3 square root of 5 plus 16/3. If you want to think of it, this is 3/3, right? So 3/3 minus 10/3, that's negative 7/3 square root of 5 plus 16/3. I could just put it all over 3, right? 16 minus 7 rad 5. I think that's as cute as it's going to get, you guys. There's our simplified answer. And yay, algebra. If this was a moment of weakness for you, simplifying these radicals, then go to my intermediate algebra video lectures. Or I have a whole playlist, Algebra Review for the Calculus Student, where I just go through how to simplify radicals, how to factor, all that jazz. It's made for you. Okay, I've got one last example. Are you ready? I know our time together has come to an end. We have integral of e to the 2x times cosine 7x dx. This is a classic problem. And this one does what we call boomerang. So you'll see what I mean when we go through the process. We have to do integration by parts twice, and we never actually end up evaluating the integral. It just comes back to us and we solve for it. You'll see what I mean. This happens anytime you have the product of two functions and their derivatives are cyclical. Like we know the derivative of e to the 2x always involves e to the 2x, and the derivative of cosine 7x cycles through sine 7x, cosine 7x, with some signs switching here and there, but it's cyclical. So that's when the boomerang situation is going to happen. So let me show you. It doesn't matter how you set up the problem because the boomerang will come back no matter what. I'm just going to set it up so that u is e to the 2x and dv is cosine 7x dx. But you could do it the other way around, believe it or not. Okay, du, don't forget the chain rule, 2e to the 2x dx. And then v would be, very good, 1/7 sine 7x. So this integral that I'm solving for, I'm going to call it I. It's equal to uv, so that's 1/7 e, oh, it's a very ugly e, excuse me, e to the 2x sine 7x minus integral v du, and I'm going to take 2 times 1/7 outside here. And then I have e to the 2x sine 7x dx. Now, is this integral any simpler to evaluate than the original? No. It switched from cosine to sine, but that didn't help. But it did. We're going to do one more round, and then you're going to see our integral is going to come back to us. Our little boomerang will return. That's why I'm calling it I, because watch for it. It's going to come back. So we're going to do integration by parts one more time with this integral here. And we've done this before, so we have to call it u bar and dv bar. Now here's my word of advice. Listen up, listen up. My teachers never told me this. If you picked u to be the exponential function the first time, u bar needs to be the exponential function the second time. And then if this was the trig function the first time, dv, then dv bar needs to be the trig function. If you have them switched, then just switch them the second round. Just be consistent. If you're not, what ends up happening, and this is the part my teachers didn't tell me, I've realized it, is you end up undoing what you just did and you go back to the original problem. Okay, so just be consistent in both rounds. Exponential, exponential, trig, trig. Or if you went the other way, then stay the other way. Okay, du bar would be, again, 2e to the 2x dx. And then v bar, this time be careful, negative 1/7 cosine 7x, right? Okay, good. So our original integral is equal to 1/7 e to the 2x sine 7x minus 2/7 is still sitting there. Then again, we have u bar v bar. So that's negative 1/7 e to the 2x cosine 7x minus integral v bar du bar. Oh, see that extra minus sign? I'm going to make it plus Oh, and I want to put the 2/7 in the front as well. So let's do all that. We're doing the most. E to the 2x cosine 7x dx. Okay, but you guys, do you see? My boomerang has returned. Hooray! E to the 2x cosine 7x dx. That integral, here it is again. And think of it now like I'm trying to solve for this quantity, which I'm calling I. So I'm going to come in here and I'm going to replace it with, you betcha, an I. All of that is I. So watch this. So I on the left equals 1/7 e to the 2x sine 7x. Let's distribute, plus 2 over 49 e to the 2x cosine 7x minus 4 over 49 I. Ooh, okay, look at us. Now let's try to solve for or isolate I. I'm going to add 4 over 49I, 4 over 49I. This is 1I, which is 49 over 49, plus 4 over 49 is 53 over 49I. And all of that is 1/7 e to the 2x sine 7x plus 2 over 49 e to the 2x cosine 7x. We're almost there. Hang tight. To get I by itself, let's multiply both sides by 49 over 53. And now we have I equals, distributing through, this would be 7 over 53 e to the 2x sine 7x plus 2 over 53 e to the 2x cosine 7x. And then here's the awkward moment. You have to go, oh, this is an antiderivative. So I have to put plus c because there were no limits of integration. You could be done. Let me rewrite what the original problem was. Integral e to the 2x cosine 7x dx is equal to all this. If you want to simplify, you could factor out the e to the 2x over 53, and then you have 7 sine 7x plus 2 cosine 7x plus c. I think that's a little cleaner. Okay, but both are correct. So that one's going to take practice for you to get down, but once you do, you should be fine. Also, a lot of the time students get confused and they go, how do I know when I should do integration by parts? I have a whole video dedicated to when to do U-sub versus when to do by parts. I'll link that in the description. And then also it's practice. So the more you practice, you'll recognize patterns. And then in the future, you'll know which integration technique to use. But the learning curve maybe is a little more steep in the beginning, so you might be frustrated, and that's normal, okay? Don't get upset with yourself. No one comes out of the womb integrating by parts. You got to practice, and then it becomes very easy breezy. So I hope you enjoyed the video. Give it a thumbs up. Share it with whoever you think would enjoy it as well. And please subscribe to my YouTube channel if you haven't already. Follow me on Instagram, TikTok, Math with Professor V. I'll be back sooner than later with more content, but I already have, I think, over 1,000 videos. They're all organized into playlists, so you've got plenty to watch while I get busy. I still teach full time, but I make these videos whenever I have a moment to breathe to help you all. Okay, love you.